Good afternoon. This is Dr. Qusay Faisal with you. We are going to start with the new topics today in computer architecture. We call it memory system. So, as I mentioned previously in Moore's law, if you remember, I said in Moore's law in first lecture or second lecture at the beginning of computer architecture, I said that every year the microprocessor speed and performance every 2 years get double. Every 2 years it increased to double. However, if you come to the RAMs and memory, every 10 years get double. And it have been many years since 1975. It started from 1975 up to now. You could find out that the performance of microprocessor is getting way too fast comparing with the performance of the memory. So the memory speed is considered as too slow comparing to the microprocessor, and thus make a problem because the microprocessor speed is too high, the memory is getting too low comparing to the microprocessor speed. To come over this problem, so the scientists create something called virtual memory. So before I go to this one, let's go through the virtual memory. What is the virtual memory? Actually, this topic I am planned to explain next lecture, not today lecture. So the next lecture it will be after the midterm theory test. So if you see here, the scientists or the technology came up with this graph, where virtual memory, it's like main memory, like hard disk or flash memory or CD. All these considered as a virtual memory. The main memory, we call it DRAM or dynamic RAM, which is normal RAM. Cache memory, this is the memory which is called static RAM, SRAM, or we call it ROM, read-only memory. So this is cache. And this is the microprocessor on top of it, because the microprocessor is too fast. However, the cache or ROM, or we call it SRAM, so this will be fast, but the problem with the cache, it's expensive. Why? Because it's used expensive technology. For that, it uses smaller memory. So it's fast, expensive, and uses small memory. However, there is a main memory which is RAM, dynamic RAM, DRAM. The DRAM is a little bit slower than the ROM. ROM is faster, little bit slower than the ROM, but it's cheaper than ROM. Also, the memory is high. So, for example, the ROM, the cache, we call it cache or ROM, maybe maximum now is 4 gigabyte. Previously it used to be 2 gigabyte, but nowadays there is 4 gigabyte for cache. That's the good, powerful computer, 4 gigabyte cache, and this is give you good for opening for games, all these things, programs which need fast movement. Okay. However, for RAM, maybe nowadays there is 8 and there is a 16 gigabyte RAM. Okay. Virtual memory, this is hard disk or CD. Okay. The hard disk, could have 1 terabyte hard disk. So that's the plan. Now to do that, the cache memory or the cache or the ROM or SRAM, static RAM, this is very close from the microprocessor, okay, and very fast. And for the RAM, it's slower a bit. So if we get back to the today presentation, so this is, we call it upper level, which is cache, which is named SRAM, another name SRAM, or we normally name it in our normal life, we name it ROM, read-only memory. And the lower level memory, which is dynamic RAM, DRAM, which is, we name it random access memory. That's the normal random access memory which we know it. So upper level memory is, as I mentioned, is very fast, high speed, with the speed of 10 nanoseconds. The data is 10 nanoseconds to access, to get, access the memory. Access the memory, which is access information, which is saved inside this memory, very fast, 10 nanoseconds. However, the memory is too small, okay? So cannot hold too much information. For that, we developed something which is slower than the upper level memory, but could hold more information. That's called RAM, which is random access memory, or a scientific name DRAM, dynamic RAM, dynamic random access memory. However, this is cheaper than this. So the problem with this one is expensive, so we go for this one, which is cheaper. Now, this is need to calculate how much time to access to upper level memory. The time which needed to access to this memory is, you see here, this is upper level memory, this one. The upper level memory is close from the microprocessor. So here is the microprocessor, as I showed you in the diagram just before. So it's close from the microprocessor, is smaller size of the memory, but is very fast and is very expensive, because the technology to make this memory is very expensive. However, we go to something called lower level memory, which is bigger size than this one, but it will be slower, and the technology which used to do the RAM is cheaper. So if you want, for example, extra RAM, you could buy it from Ali Namali, that we say 40,000, 30,000 dinar. Okay, you could buy another 2 gigabyte, but it's depend on your memory, your motherboard, how much accept. So, and if it have extra slot to put extra RAM. So the RAM for let me say another 2 gigabyte may cost you something like $40,000, 40,000 Iraqi dinar. But if you go to room, you cannot buy extra room, because normally room are built in, the cache are built in. It's possible to buy extension, it's possible to buy extension, but that would be costly, too much costly. I think it will cost you maybe $200, $300, is depend. So you could buy, not built in, you could buy extra outside, to link it with UPS, to link it with USB port, okay? But that would be costly. However, now we are going to talk about the time. The time actually to access to upper level, we call it hit. So hit rate, so now if we go to upper, so hit rate is the fraction of memory access found in upper level. So the hit rate is the time to access to upper level memory. So the time to access to here, we call it from the microprocessor to access to here, we call it upper level. We call it hit rate, because we found it at the upper level, at the RAM, at the S, we call it SRAM, static RAM or room. So the hit rate is to access to upper level consists of RAM access time plus the time determined. Hey guys, this is last lecture before the midterm. This definition you do need to memorize it. So what is the miss rate? Sometimes the information is not saved at the room, not saved. So let us say if you go for Windows system is saved inside the room. So when you open the computer, the BIOS straight away, first of all, when he wake up, the computer wake up, will go to the room, which is, we call it static RAM, SRAM. This is a scientific name for room, is SRAM. So it will go, so the computer when switch on, first of all, is going to go to boot system, which is available, all the boot system is available in upper level memory, which is saved inside the room. So if the information is not found in the room, the microprocessor is going to search about it where? In lower level memory, which is in RAM. So RAM also will save the address memory for most common information you have opened. So for example, when you open Word, PowerPoint or something like that, the address of the information is saved inside the lower level memory if it's not saved inside the room. So first of all, it's going to search about it in room, then from microprocessor is going to search about it inside the RAM, which is the RAM also fast, but not as fast as the room. And it's also used expensive technology. So less expensive technology. It's expensive, but it's less expensive technology than the room. However, so we if don't find the information inside the upper level, is going to search about it inside the lower level. See here, miss rate when data need to be retrieved in the block in the lower level. So the microprocessor didn't find the information inside the upper level, inside the room, is going to go to dynamic RAM, or we call it RAM, is going to search here. And thus we call it miss rate. Why? Because the microprocessor, he missed the information, he didn't find the information in the upper level. So it's going to search about it in lower level. Lower level we name it block Y. So miss rate is equal to 1 minus the hit rate. So the hit rate we know it. So it's about, let me say 10 seconds. So 1 minus the time which is taken in the hit rate. So it will be the miss rate. However, sometimes the information is not found in the lower level too. Okay. Why? Because maybe the information didn't open for very long time. Let me say this information used it, let me say 1 year ago. So the address of the information is not saved here. However, the microprocessor is going to take long time. He's going to take time to search about it where? Count to call it from the main memory. Okay, so it's going to take more time. That's what we call it penalty rate. So penalty rate is to replace block in upper level. So when it's going to search in the main memory, so it's going to find the address of the information in the main memory, is going to save this address where? In the lower level. Okay, it's going to save it inside the RAM. And then it's going to replace one of the information which is already saved inside the RAM, is going to replace the address of the information which is saved inside the RAM with the information which you just open it now. Okay, so the time to replace block in upper level plus the time to deliver the block to process. So time to replace the block from the address, the address of the information in the main memory is going to put it in the block of the lower level, and plus the time to reach the information inside the microprocessor. So this time we call it miss penalty. So if the information not found in the lower level, so this is penalty, miss penalty. Is going to search for it in the main memory and going to put the address if he find it, of course. After he finds it, he's going to put the address of the information which is available in the main memory, is going to put it in the lower level. So this is going to take time to replace and is going to replace one of the information which is reuse it, very low use it, is going to remove it and put the address of the new information inside it. And then plus the time to deliver to the microprocessor. So this is, we call it miss penalty rate. Guys, this definition, the hit rate, miss rate, and miss penalty rate, you do need to memorize it because it's one of the questions. Definition. What's the definition of miss rate? What is the definition of penalty rate? Maybe I ask you, what is SRAM? SRAM is a static RAM, or we call it ROM, read-only memory, which is called the upper level memory in virtual memory. And what is DRAM is dynamic RAM, or we call it random access memory, and this is block Y, which is lower level memory. So these are all at definition, you need to memorize it. The temporary location, if unreferred, when you reference item, okay, you find some information inside the main memory and you put it as a reference in low level memory, in RAM. So the RAM, what is going to do is going to save the information which you just open it in the main memory. It's going to save the address of the location. So this is going to save it. This is, we call it temporary location. Now if this information is going to be open too much, what's happened is the microprocessor, or the information the address of the information is going to save where? Automatically is going to save in upper level memory. So if you open, for example, Windows too much, if you open PowerPoint document too much, so the PowerPoint document or Windows document is going to, the address of this document is going to be saved in upper level memory, which is in room, so to be opened too fast, okay, or faster than before. So when it's saved inside the room, so the microprocessor is going to search for the address which is available in room, so it's going to open too fast, faster than before. So this is, we call it special location. So temporary location, when the memory is saved in lower level memory. Special location, no, now it's become special, so it's going to open too fast. So the address of the information is going to save in upper level memory. So that's the difference between special location and temporary location. Temporary location is saved here. Special location is saved inside the SRAM. Okay. So let me see here. If an item referenced, it will be tend to reference again soon. Keep recent information closer to the processor here. Location, if item referenced item whose address are close by tend to be referenced soon. So here, close to be closer here to the upper level memory. Okay, and you are going to move the address of the information from the block Y, you are going to move it to block X. So this is special location. Now this is about the temporal location and special location. As I mentioned, DRAM, called dynamic random access memory, which is, we call it DRAM here, block Y. This is the lower level. We call it in the market, we call it RAM, random access memory. This is high density, okay, but the technology which used to make this one is low technology, because it's cheaper technology. So it's low power and slow in speed. Okay. So that's for DRAM. SRAM, or static RAM. This is, we call it in the market, we call it ROM, read only memory, or we call it cache. Okay. Which is here, I name it upper level memory, block X. We call it cache memory. In the market, we call it cache memory. Or it's same, we call it ROM, read only memory. So this is the capacity of the memory is low density. It's only 2 gigabyte. Whether RAM, DRAM, you could find it 8 gigabyte easily. 8 gigabyte now in the market, available easily. There is 6 gigabyte, there is 8 gigabyte. And you know, I think there is 16 gigabyte, but this is expensive, you know, with high specification. But there is, but impossible to find cache, impossible even now to find cache with 16 gigabyte. Maximum cache, I think 6 gigabyte, but 6 gigabyte, this is expensive. Okay, and normally is built in. However, there is some cache which is use ESP port. Okay, there is, if you want to extend cache, but it will be with a few extension. You could extend with only 2 gigabyte more, you know. No, you cannot get any more cache than that. Okay, we call it also ROM, read-only memory. It's same. So, however, the capacity is low density, the power high power, but using very expensive technology. The technology is costly. That's why it's expensive, because it's too fast to make it very fast. So this is static. Okay, so that's DRAM and SRAM. So in midterm exam, I might ask you what is DRAM, what is SRAM. Okay, so you should know. So this is the virtual memory. Okay, so this is the virtual memory. First of all, we have CPU, central process unit, which is consist of registers. The speed of registers is 1 nanosecond. This is SRAM. Okay, SRAM or cache, or we name it ROM, read-only memory. Okay, so static RAM or cache, or we name it also the upper level, block X. See here, the upper level, this one. Okay, block X. So this one is very very close from CPU. Here the speed is also 1 nanosecond. The main memory, we name it DRAM, dynamic RAM, or in the market we name it RAM, only RAM, random access memory. Now here in the graph is the lower level memory. See here, this is DRAM, or the main memory. Now here, this one, as I mentioned, the speed is less, but is acceptable. 10 nanosecond is okay. The memory is less expensive. The cost of it is less expensive, and the memory is higher than this, but is not too high. It's still just 8 gigabyte. Just 8 gigabyte of memory is cannot hold too much memory. However, there is the main memory. Okay, the main memory, or the virtual memory. This one we call it. The hard disk could be the CD, could be the flash memory. So this is the flash memory. Flash memory is something like that we say 500 gigabyte, or the main memory 1 terabyte. 1 terabyte is possible for the main memory. So this is the design of virtual memory. We are going to talk about it more in the lecture after the midterm. More details in the lecture after the midterm. Now this is the virtual memory. See here. So this is the CPU is here at the top. We call it central processing unit. Okay. Then the small size memory, which is the we call it the DRAM. Okay. Then after that comes the CD, flash, and at the end here so here the hard disk. Of course, the hard disk is power off. Okay, so you do need it's going to be on when the microprocessor is going to call it to take more information. Okay, otherwise it's off. But the RAM and the ROM always on. Okay, then after that there is something example for very slow, we call it tab backup. So tab backup, you put it outside and you link it with the computer. So these are called the virtual memory. This is the level of memory hierarchy design. Memory design. Now let's come for the midterm tests question. Now what about midterm test question? You have I will not go out of the computer architecture question which I give you. Okay, some of the question I give it to you in the midterm. So what is the computer architecture? So this is definition, ta'rif. So what is the computer architecture, and what are the computer architecture includes? What is define the computer architecture and what includes? So this is one of the question could come. Okay, so the computer architecture is referring to how computer system is designed and what technology compatible with. What we are going to do now, we are designing computer where we put the CPU, where we put the cache, where we put the RAM, and after that we are going to do mapping to the memory, how the memory mapped inside the memory. So this is after the midterm. So and what includes? So VHR includes 3 levels. So you just need to write this one, coordinate level of abstraction, merits of abstraction, okay, and under set of changing forces. No need for explaining this one, okay. So just this includes 1, 2, 3. No need for drawing. This drawing I will not ask you about it. So this these are definitions: system design, instruction set, architecture, micro. This is all definition. I might ask you about definition. Define the following. Now this is the clock rate, and this is about the Morse law. I defined Morse law definition. You find it here somewhere. Here I wrote the definition of Morse law. I think, and somewhere there is definition of Morse law. The clock rate. What is the definition of a clock rate? This is the define of a clock rate. Yes, this is the definition of Morse law, which I talked about. Okay, and as I mentioned today, I mentioned in today's lecture, that the memory double every 10 years, while the microprocessor speed and powerful every 2 years. So that's make big gap between the progress of the memory and the microprocessor. So this the big gap. To overcome of this gap, okay, because now the microprocessor is very powerful, very high speed, and the memory considered very slow comparing to the microprocessor. To make up this gap, so we went to something called virtual memory, which I explained today lecture, and calculate the miss rate, hit rate, penalty rate. All these things have been calculated. Computer design. I think this is question came to the quiz, which I just did it last week. So what is the computer design? Divided into instruction set design and computer hardware design. So this came in the quiz last week. Instruction set. I am not going to give you anything about this topic. This one. All these things don't need to read it. Okay. No need to read this one. Page number 4. So again, page number 4. Don't need to page number 4. Okay. For instruction set architecture, I will ask you about this. Okay. This you do need to memorize it. So what is instruction set architecture? So stages. So you have these stages. Okay. This you do need to memorize it. Okay. But the summary of computer architecture, this one, no need. Okay. So please don't read this. In page number 4, for the summary computer system components, no need to read it and waste time. I will not get it in the exam. Okay. So this one, no need to read it. Again, page number 4, no need to read it. Is not come to the exam. Now, structure of von Neumann diagram. This is very important. Just read it, and this is the design. Very easy. The design is main memory, and this is arithmetic logic unit, and this is central process unit, and this is input output. So this is how to connect between the design. This is basic, and all of you know it. Okay. The main concept of the von Neumann diagram. So this is the main concept. I may ask you, what is the design of von Neumann? I will not ask you for this. This one is not going to ask you. I will ask you, what is the structure of von Neumann diagram, and what it includes? What's the main concept? So this is the structure of von Neumann diagram, and this is the main concept. 1, 2, 3, 4, 5, 6. 6 concepts. So this one, it may come in the exam. Okay. In the exam, I may get you one of these two things, either this or this one. Okay. So if you have this or this, I will ask you, what is the von Neumann diagram structure and the main concept? So this is the von Neumann diagram, and this is the main concept. Or I will ask you, if this question not come, I will get you this question. If this question not come, I will get you this question. So design, okay, the set register of the structure of ISI mechanism with small explanation. Okay, so this is the set diagram of ISA mechanism. Small explanation. I don't want you to explain the definition. I don't need this definition. I just need, for example, small explanation. I do need, for example, MBR. So you just write MBR memory buffer register. MBR memory buffer register. Or you could draw line, draw arrow on MBR and write memory buffer register. Just draw arrow. Okay? Or write this one. I don't need definition. What is MBR? What is the memory? I don't need this. Okay? In the exam, I don't need this. I need the design, the structure of this one, the structure of ISA mechanism, and the definition of each one. So what is MBR? So MBR memory buffer register. What is memory address register? What is MAR? MAR here down. MAR. This one. MAR. MAR is memory address register. There is something called IR, instruction register, or IBR. IBR at the top here. So IBR, instruction buffer register. So this definition I do need to show it when you give me the structure of ISA. This is the structure of ISA, and I want the abbreviation of these things. AC, accumulator. What is accumulator? So I think AC, this is accumulator. You know it during the quiz. So these things you do need. I don't need the definition of these things, but I do need what is these things names. Okay. Then after that, other questions. This one, page number 7, I will not bring it to the midterm test. Page number 7, all page number 7, no need to read it. All page number 7, I am not going to bring it to the test again. No need to read it. You go for page number 8. Page number 8. Page number 8 also you don't need to read it. Page number 7 and 8 you don't need to read it. It's not coming in the midterm test. Okay. You go for this one, design as a refreshment. This is as I explained in the video. You could look to the video. Is explained already. So this is may come. This is may come. So page number 9 may come. Okay, and then you go for page number 9, 10. This is may come. Similar as I explained in the videos. Okay. Now, if I will go to the question, is better. Yes, this one here. Sorry, this is the question. So the question, you see, this is the question. Question number 1, question number 2, all this comes. Question number 3, the definitions, all this comes. Okay. Question number 4. Okay. Okay. So you could see here. This is the structure, and I might ask you for abbreviation for this structure. Okay. The six organs. What is the main concept? Sorry, these are the main concept of Van Neumann diagram. I will not get you this. This is not needed. So what is the structure of Van Neumann diagram and what is the main concept? So this is the main concept and this is the structure of the Van Neumann diagram. Let's go for this one. So this is in the question. This is page number 4. What is ALU? Okay. What is the design of requirement? This is same as I explained in videos. Okay. So all this includes. This is the half adder and full adder. You know how to get the half adder. So you have this is X and Y. This is 0011 and 0101. So if you put sum and C out. So 0 plus 0, so 0, and how much left is 0. 0 plus 1 in binary is 1. Summation of 0 plus 1 is 1, and there is no remainder. Okay. 1 plus 0 also is 1, and there is no remainder. 1 plus 1 is 2. 2 in binary is 0 and 1 remainder. So this is C out. How to present it? So is presented for sum for S. This is when sum is activated. Sum is activated when is 1 when is X toggle or X dash Y. So this is X dash Y plus what? Plus X Y dash. X Y dash. Now this one is I think it will remind you. You studied logic before. It will remind you X dash Y plus Y plus X Y dash. This is remind you about XOR. So this is X XOR Y. This is remind you about XOR game XOR gate. So this is X XOR Y. So and C, when C is 1, C is 1 only when X and Y. So only when X and Y. So this is AND gate. So this is X AND gate. This is give you C out. XOR gate. So X XOR Y give you sum. Same how you do the truth table for full adder. So full adder gate. So I might ask you draw the truth table showing the diagram gates for full adder. So this is the full adder. So full adder you have X, Y, and Cn. So you have 3 inputs. So 0 0 0 0 you have 4 zeros for 1, 2 0 2 1 2 0 2 1, and 0 1 0 0 1 0 1. Also you have sum and C out. So 0 plus 0 plus 0. So give you 0 and C out is 0. 0 plus 0 plus 1. What is the result? Is 1. The output, there is no remainder, 0. 0 plus 1 plus 0, how much? So is 1. There is a remainder? No, there is no remainder. Remainder is 0. 0 plus 1 is 2. 2 in binary, actually is 0 and there is 1 remainder. 1 remainder, so this is C out is 1. Okay? So 1 plus 0 is 1. There is no remainder. Okay, 1 and the remainder is 0. 1 plus 0 plus 1. 1 plus 0 is 1. Plus 1 is 2. 2 in binary is 0 and there is remainder is 1. So this is the remainder here. C out is the remainder actually. 1 plus 1 is 2. Plus 0 still 2. So 2 is 0 and the remainder is 1. 1 plus 1 is 2. Plus 1 is 3. 3 in binary is 1 and the remainder is 1. Okay? And how you present it? So that's how you present it. So see here, where is S is 1? S is 1 is here. So here is X toggle or X invert, Y invert, Cn. So X invert, Y invert, Cn. And where else? Here. Here is X invert, Y, and Cn invert. So here X invert, Y, and Cn invert. Where else? Here we don't consider it because it's 0. Here is 1. So here X, so see here, plus X. And what is else? Y invert, Cn. So Y invert, Cn invert. See here? Where else? Here. Here is 1. So where? X, Y, Cn. X, Y, Cn. And you summarize it, you get that S equal to Cn XOR X or XY. So this one. C out, where C out is 1? Is here. Where is here? Where is X invert Y Cn? So X invert Y Cn plus. Where here? Where else? Here. Here is 1. So here X Y invert Cn. X Y invert Cn. See here? Plus where is 1? Here as well. So X Y Cn invert. X Y Cn invert. This one. Where else? The last one here. X Y C. So where is it? X Y C. Here. X Y Cn. You summarize it, so you get Cn dot between two bracket X XOR Y plus XY. So if you just draw it in diagram, so that's what it will be. So this is for sum and this is for This is for sum and this is for C. And see here, very easy. And I explained in video. You could look at it in video. So this is just revision. And then also I explained how to do arithmetic, how to do full adder using the arithmetic logic unit. That's how we do it, addition, and that's how we do subtraction. Where is it? Here. Here when we do the subtraction, you do need it to put the motor equivalent to 1, and the second number you put it with XOR, okay, to make the invert. So you are going to do subtraction. Because arithmetic logic unit don't do subtraction, do only addition. But how it's going to do subtraction using full adder? It's going to do XOR for the second number to make the invert, okay? To make the invert for the second number added with the first number, and it's going to put the C in with 1. So do invert plus 1. So same like when you do subtraction, okay? So that's I explained in video. You could look at the video for how you do full adder subtraction in arithmetic logic unit. Also, I explained how to do the zero flag or overflow flag inside the memory, zero flag or overflow flag. Then after that, I define the MIPS. I think MIPS is one of the abbreviation come to the quiz. So this is the definition of MIPS, okay? And this one, find the multiplication to make it easy for you, okay? I'm not going to bring the I'm going to bring the process of multiplication. I am not going to go for design multiple hardware. So question 23, I'm going to give it to you in the exam, okay? But 24, okay, and 25, I'm not going to bring it in the exam. 24 and 25 is not included. I'm not going to give you the design, although I explained in one of the video, okay? Maybe I'll bring it in the final, but not in the midterm. In the midterm, just I want you to read first now. Read whatever you have. Look to the video. Return back to the video. So I'm not going to give you question 24, 25, but question 23, I am going to ask you. I will give you two numbers, you multiply them. Very easy to multiply two numbers, should be very easy. Or I give you two numbers in binary, I want you to divide it, okay? Divide it. But I'm not going to give you design hardware for design division hardware for version 1 and 2. I'm not going to give you design division multiplication hardware for version 1 and 2. This one, question 24, 25, I'm not going to give it to you, just to save your time and make it easy for you. Same for question 27, 28. I'm not going to bring it to the exam. So 24, 25, 26, not going to come, 24, 25, not going to come to the exam. 27, 28, I'm not going to bring it to the exam. I'm not going to give you design, okay? But 26 is going, so I'm going to give you two numbers in binary, and I want you to divide it, okay? Just do long division, okay? I'll give you two numbers and multiply them, okay? This is going to come to the exam, okay? Question number 9, page number 9, the pipelining. This is the video, which is just the week before the quiz. You remember, I explained video. So this video and some of these questions comes to the quiz. You know, this question basically. What is the pipeline stages? Okay, there are 5 stages: IFID, which is instruction fetch, instruction decode, operation fetch, operation OE, and operand storage, operand what's name here? Operand execute and operand store. So these the 5 stage of pipeline. What is very important? What does each stage do? So you do need to memorize them, okay? So that's the concept of pipelining. This is the stages of pipelining with explanation. And maybe in the exam, maybe I will tell you, explain, this is for 3 stage, okay? These are for 3 stage. How much cycle you saved here in these 3 stage? You saved here, you required 15, here you required 15 cycle, over here you required only 7 cycle. So you saved something like 8 cycles saved. So maybe in the exam I would tell you to do for 4 stage, okay? So you do need 4 instruction. So this is instruction 1, instruction 2, instruction 3. Maybe you add 4 instruction or 5 instruction. So you do it for 4 instruction or 5 instruction, and you calculate how many cycle you require, okay, for all instruction. So you know what is the time you required, and how much if you do the pipelining. So I might ask you to do, instead of 3 instruction, you do it for 4 instruction or 5 instruction. Check how much you save time for pipelining. So this are also one of the questions. So what is the parameters, important parameter in the pipelining? And what is the advantage and disadvantage for pipelining? These are very important as well. I think in the exam I give you, in the quiz, I give you one of the true and false for advantage and disadvantage, true and false. Now in the exam, midterm exam, I will not give you true and false, but I will give you just write the advantage and disadvantage for pipelining. Question like that may come, okay? In page number 10, and this one I'm not going to ask you now. Maybe this is question for the final, not for the midterm. But I'm going to ask you about the definition, which is today lecture. So what is the miss rate? What is the hit rate? What is the penalty rate? Okay? And this is the design. This is how you design. The level of hierarchy level of computer. So you have here the microprocessor, here the upper level, this is the lower level, and the definition, miss rate, hit rate, miss rate, and penalty rate. These are very important definition, okay? Because from this, after that, next lecture, will lead us to next lecture, okay? So this was today lecture. In midterm, I'm not going to ask you about question number 34, okay? But 35 you might have question number 35, which is today lecture, okay? That's it for today lecture. Tomorrow lecture I'm going to do revision. So either you come to the university. I think you have midterm exam. So either you come to them after the midterm exam, midterm practical exam. You could ask me, I am available, or I am going to upload another video again. This video just revision for and prepare you for midterm questions, same like what I said now. So that's it for today lecture. Thank you to all and have a good time. Bye.